Hello and welcome back. In Unit 4 we are going to discuss digital circuits, and we're going to take some of the basic gates that we looked at in Unit 3 and we're going to put them together to create digital logic circuits to produce specific functions. So again, in this first unit we're just going to review the AND, OR, and NOT gates and also buffers that we learned about in Unit 3. We're going to make sure we're familiar with the symbols, the truth tables, and the Boolean expressions. Remember that in the later part of the 19th century, George Boole frustrated his colleagues by suggesting that logical thought could be represented through mathematical equations. The thought was, how dare anyone take something as complex and unique as human action and human behavior and human thought and boil it down to mathematical equations and yes-no answers. However, computers as we know them today are implementations of Boole's law of thought. Everything can be broken down to simple sequences of yes or no and combinations of inputs. The first gate we're going to look at is a buffer, which is just as the name implies, it just passes the input to the output. The Boolean expression then is y equals a. If y is our output over here, it's going to equal whatever the input is coming into this thing. The truth table also shows that. Remember, a truth table shows all possible input combinations and their associated outputs, and we can see that the output follows the input as is. The next gate we're going to look at is a NOT gate, or a simple inverter. I'm going to use the terms NOT gate or inverter interchangeably, so keep in mind that they both mean the same thing. The Boolean expression for an inverter is y equals a naught. That bar over there, over top of the a, means that the value is inverted. And the symbol is the triangle with the bubble on the end, as opposed to the inverter in the buffer in the previous slide. The inverter has a bubble on the end. That bubble always indicates that something is being knotted or inverted. And so if a over here equals a 1, the output y will equal a 0. Or if a equals a 0, y will equal a 1. It will take whatever the input is and invert it for the output. Some alternative notations, especially if you're typing up assignments and so forth, y equals a naught, or y equals a with a little tilde character preceding it. Those also mean the same thing as a with a bar over it. And we can see from our truth table, our one input inverter, the input is a 0, the output is a 1, and vice versa. The output follows the input inverted. One of the other gates we looked at in Unit 3 was the AND gate. Recall that the logic symbol looks like this, and in this particular depiction we have a 2-input AND gate, inputs A and B, with an output y. The Boolean expression is y equals a times b, and it's also written without the dot notation. Remember that multiply always implies an AND operation, so if you see two input variables multiplied together, whether we're using the dot notation or we just write them side by side, both of those mean multiply, and if that's the case, we are talking about those variables being ANDed together. Taking a look at the truth table, we saw this before in Unit 3. Notice that the first three input combinations, 0, 0, 0, 1, and 1, 0, all result in an output of 0. If anything going into an AND gate is a 0, the output is 0. But if all of the inputs are a 1, the output will be a 1. So to get a 1 out, all inputs must be 1. Otherwise, we're going to get a 0. And so we're going to call that state, the only way to get a 1 out of an AND gate, we're going to call it the unique state, where all 1's in implies a 1 out. The last gate we talked about in Unit 3 was the OR gate. And again, there's the logic symbol. Again, we have a 2-input OR gate shown with a single output y. And the Boolean expression for an OR gate is y equals a plus b. Remember that add always implies or. If you see two variables added together with a plus sign, that means we are intending to or them together. Looking at the truth table, as opposed to our AND gate where everything had to be a 1 to get a 1 out, for our OR gate we notice that if anything is a 1, we get a 1 out. But if everything is a 0, we get a 0 out. So in the previous gate, our AND gate, everything had to be a 1 to get a 1 out. For an OR gate, anything can be a 1 to get a 1 out. If any input is a 1, the output is a 1, otherwise we get a 0. And so our unique state is the input combination that gives us our unique output. If both inputs are a 0, we will get a 0 out. Now also remember that AND and OR gates are not restricted to 2 inputs. Truth tables for each of these gates can be extended to 3, 4, 5, however many inputs we want. And that's because for an AND gate, the rules are the same regardless. If everything is a 1, you're going to get a 1 out. If anything is a 0, you're going to get a 0 out. So it doesn't matter how many inputs, all the inputs have to be a 1 for an AND gate to output a 1. Otherwise, if any of our inputs are 0, the AND gate will output a 0. Similarly for our OR gate, if anything is a 1, we'll get a 1 out. If everything is a 0, we'll get a 0 out. The unique state remains the same regardless of the number of variables. So now please go complete the online assessment so that we know you have a thorough understanding of those basic gates before moving on to the next node, where we will discuss NAND and NOR gates.